See there. Question 32, we have group 4 elements. So group 4 elements, carbon, silicon, and germanium, they all have giant molecular structure. Giant molecular structure is the same as giant covalent structure. So they have a lattice because of the giant structure, repeated network throughout. But their lattice particles consist of atoms because these are forming covalent bonds. So the atoms share electrons. What can we say? The bond length are getting shorter. So it gets shorter from here to here, but then it get a bit longer again. Why does the bond length increase down the group? Does it get longer or shorter? No, it get longer, sorry. Yeah, I see it now, okay? So this is 0.15, 0.23, 0.24. So the bond length increases. So the covalent bond gets longer. The bond length increases as a result of more shells. Definitely as you go down the group 4, any group, you get more shells occupied with electrons because that is what period number tell you after all. If we get more shell occupied, the distance between the nucleus, so the internuclei separation, so between the carbon-carbon, between the silicon-silicon, between the germanium, the internuclei distance will have increased. That is a result of the more shells occupied, the bond length increase, the distance between the two nucleus, such as if I am over exaggerating, I would do like this, then the nuclei are getting further and further away. So looking at number 2, atomic radius increases down the group. That is actually one of the reasons because the atom is getting bigger. How about number 1? So orbital overlap decreases down the group. So orbital overlap decreases as you go further down. The nucleus is getting further and further away from each other. Bond length. What affects the bond length? Orbital overlap decreases down the group. This is to do with bond strength. So we know that bond strength is related to bond length. So bond strength increases as bond gets weaker as bond length gets shorter. So shorter bond, this is a shorter bond. Shorter covalent bond means it's a stronger covalent bond. This is as stated in the covalent bonding syllabus in your Cambridge curriculum. So the fact that your orbital overlap decreases, your covalent bond gets weaker, and your bond length will increase there. So 1 is definitely correct as well. Number 3, your nuclear charge does increase down the group, but having said that, that should surely make the size get smaller as it pulls them closer together, but it doesn't. In fact, the size is getting bigger because of more shells occupied. In reality, your shielding will have increased significantly going down the group. So only 1 and 2 are correct. Therefore, there must be statement number B there. Question 33, we have the salt NaClO3. This is actually called sodium chloride 5 because of the formula, and you know about oxidation number. Oxidation number of a compound is 0. For sodium in a compound is +1. Chlorine is what you want to find. 3 of the oxygen, each of which is -2. Each of the chlorine is chlorine +5. That is called chlorate with the ATE and then a V there to represent the +5 oxidation number. So on careful heating, this is what happened. You now have chlorine -1. And how about the NaClO4? 0 for the overall compound, +1 for the sodium. And then chlorine is what I want to find. I have 4 of these oxygen, each of which is -2. Chlorine there is +8 -1 is +7 there. So what can I say? I can say that the first one is a disproportionation because this reduced to chlorine -1. This oxidized to chlorine +7. Now the NaClO4, as what I had shown you previously, is chlorine +7, and then this is chlorine -1. So this second reaction here is not a disproportionation, but it is simply a reduction. Well, it's a redox actually. It's a simple redox because it's not just reduction. As the oxygen -2 go to oxygen 0, obviously. The first one is a special kind of redox. It's called disproportionation, where one species get both oxidized and also reduced in the same reaction. Both of them are redox reaction, by the way. This overall reactions, chlorine -1, oxygen 0, chlorine +5 there. So what do these equations show? These are the overall reaction, yeah? So in the first case, we always check for statement number 2. NaClO3 can be behaved as a reducing agent. Reducing agent is defined as a substance that reduces the other substance, and what happened to itself? Itself get oxidized. What do these equations show you? So this equation mean either of these equations. So do we see that itself get oxidized? This is chlorine plus 5. Does it go higher? It did go higher to chlorine plus 7. It did get oxidized. Therefore, 2 is correct there. Okay, let me just move that a little bit to the left hand side. Now, statement number 1, NaClO3 can behave as oxidizing agent. Oxidizing agent means itself get reduced. Do we see itself get reduced? Yes, in this second reaction. Yes, also in this first reaction here. So in both of these reactions, the chlorine, oops, sorry, not the second one, because second one is not the NaClO3, but the first one, the plus 5 goes to minus 1, itself does get reduced there. How about number 3? The oxidation number of chlorine in the 3 compounds shown. Well, you don't have plus 8, that is definitely wrong. The maximum there was plus 7, as I've shown you. Plus 6 is also wrong. What you have is plus 5, plus 7, and minus 1 is correct there. But 3 is definitely wrong, so you're left with 1 and 2, which is just option B. Question 34. Which statements correctly describe effect of a rise in temperature on a gas phase reaction? We know that temperature affects your kinetic energy. This is part of your Boltzmann distribution diagram, as well as kinetic particle theory. Okay, so in terms of number 2, the energy distribution profile changes. Yes, it does change. If I sketch a Boltzmann distribution, so if I have these at a particular temperature, so on the y-axis, I have the number of particles with energy E. On the x-axis, I have energy E. So if I label this as activation energy, just an arbitrary value there. Let me just put in a pink color for what happened at a higher temperature. At a higher temperature, the whole graph will shift to the right. This is the most probable energy. There are more particles having a larger, there are actually lesser particles having the most probable energy, because this pink color one, most probable energy, higher temperature. So going from there to there, the left to the right hand side, I have increased the temperature. Look also at the proportion of molecules having energy greater than or equal to EA. I have increased the area under the graph below the pink line there, because there are greater proportion of effective collisions that will undergo reaction right now at a high temperature. So red will be higher. But in terms of most probable energy, the most probable energy value is getting higher. So this is the most probable energy at the lower temperature. At a higher temperature, this value is higher, but there are lesser molecules. You look on the y-axis, there are lesser molecules having this most probable energy at a higher temperature compared to previously. So here it says more particles having more most probable energy. More particle is actually wrong. It should be less particle, because as you shift the graph to the right hand side, you increase the proportion of effective collision here, but this height would have decreased. So this value is higher, but you get lesser molecules having this most probable energy. 2 is wrong, which means only 1 must be correct there. And number 1 was based on what I've just said, based on this right hand side of the graph there. Number 3 is definitely wrong, because you don't change the original activation energy, because there is no alternative reaction pathway, unlike when you have a catalyst, which will provide you an alternative reaction pathway, right? But not in the case of changing temperature. Question 35. Which statement concerning the group 2 elements? So in the modern papers, after the 2016 revamp of the syllabus, they have scrapped off this Roman numeral, and now it's group 2, like using the number as stated in your periodic table in the data booklet. Okay, so but it's still the same group 2 chemistry. Magnesium, calcium, and barium, which about their compounds or the elements are correct. The oxidation number exhibited in the stable compound is +2. That is correct for all group 2 elements. When they form compound, they exhibit this +2 oxidation number exclusively. Their reactivity increases with increasing relative atomic mass. So increasing relative atomic mass means down the group. So down group 2, reactivity increases. That is because the valence electrons are further away from the nucleus and therefore they are less shielded. If they are further away from the nucleus, they are less shielded, and therefore it's much easier for you to lose the outer shell electrons, and that is how group 2 metal will react by losing the outer shell electrons, which become easier to be removed as you go down group 2, and therefore they would be more reactive. Number 3, on strong heating, their nitrates give off oxygen only. The only is the wrong bit because you do get NO2, you do get half O2, you do get the metal oxide, M2 plus O2 minus, from this M2 plus and O3 twice here. This is the thermal decomposition of group 2 nitrate. Balance equation is required for you to do any sort of stoichiometric calculation. So 1 and 2 is option B. Question 36, sulfur dioxide is used as a food preservative. So which statements about SO2 are correct? So we know that aqueous SO2, this is SO3 2 minus, this is called sulfite. In your paper 3, you are specifically advised to know this particular test, SO3 2 minus versus SO4 2 minus. One is called sulfite with the ITE, one is called sulfate with the ATE. These tests were also covered in your O-level, your GCSE or your IGCSE level syllabus. If you don't believe me, you can always go back to your previous year 9, year 10, year 11 kind of education and actually go through your notes and convince yourself that these are something you would have done previously. I'm going to work out the oxidation number. -2 equal to sulfur plus 3 times -2. Sulfur there is going to be -2 plus 6 is sulfur plus 4. Calculator will not show you when it is positive, but we know oxidation number, very important to have the positive and the negative in order to represent what is going on in terms of the value there. So sulfur plus 4, that is also coincidentally the sulfur plus 4 in the SO2 oxidation number. For the sulfur plus 4 there. SO3 is sulfur plus 6. If you watch my other topical playlist on periodicity, specifically on nitrogen sulfur chemistry, you know that I specify this sulfur plus 4 in the SO2. When they dissolve in water, they're going to give you H2SO3, which consists of this SO3 2 minus sulfite plus 4. When you have SO3 dissolving in water, you're going to get exclusively H2SO4, which consists of these SO4 2 minus sulfate. Both of them are plus 6 like that. So SO2 is sulfur plus 4. SO3 2 minus is sulfur plus 4. So this is actually correct. You can in fact write an equation SO2 plus H2O, the balance equation H2SO3 consisting of this SO3 2 minus sulfite with the ITE there. Now, how about option 1? We know that it prevents the oxidations, therefore it prevents your food from going bad. So it behaves as an antioxidant for this very purpose. As a food preservative, it must act as an antioxidant. Also, to act as a food preservative, it must also inhibits mean prevents or restricts the growth of mold and yeast. So all these things can make your food go bad, and therefore this is the very purpose that they can act as a food preservative. So all of them must be correct. Option A there. Question 37. So an oxidizing agent that can oxidize ethanol to ethanoic acid or to ethanoic ions will also oxidize methanoic acid. So I remember back then in 2015, this thing was not really in the syllabus then, but this thing has been added to the current syllabus in the A-level curriculum. So I think this is actually part of A2, carboxylic acids, acyl chloride, that topic, but it was briefly in the AS component. Things have been shifted around a little bit. Doesn't matter. So the very reason why you can oxidize methanoic acid is because of this fragment on the far left hand side that make it look like aldehyde. There is a hydrogen on the carbonyl carbon, which means you can lose the hydrogen. Loss of hydrogen means it is reduction. So loss of hydrogen is oxidation there. Oh gosh, okay. Anyway, you're looking for something that will react differently with the methanoic acid as well as the ethanoic acid. So I'm just gonna quickly talk about the 3 different tests, whether they will react or not. I'm gonna put a tick across based on this simple table which I have just drawn up. So looking at the second one, Felling's reagent. Felling's reagent is a test for aldehyde. So we don't have an aldehyde, do we? Yes, we do. We do have like something that looks like aldehyde fragment there. So, methanoic acid can react with Fehling reagent. It can react with Tollens reagent. When you react with Fehling reagent, you will get a brick red precipitate because of the formation of copper 1 oxide, which is Cu plus, and then O2 minus, giving you Cu2, or brick red PPT, test for reducing sugar for the presence of the aldehyde present in reducing sugar, such as in this methanoic acid. So ethanoic acid will not give you any positive result, so the solution remains blue, okay, because that's the color of the solution for Fehling reagent. So react differently, so 2 is definitely correct there. In terms of the carbonate, so carbonate, test for carbonate, it reacts with acid. Well, you will get effervescence of the carbon dioxide, which you can test for with lime water. So this is a carboxylic acid, this is a carboxylic acid. So one will react the same way for both of them. They will not react differently. One is definitely wrong. 2 is correct, 1 is not what you're looking for. So you're looking for option C, which is 2 and 3. If you look at dilute acidified KMnO form, you cannot oxidize the ethanoic acid anymore because this carbon, the carbonyl carbon there doesn't have any hydrogen left, but this carbon of the methanoic acid, there's still one hydrogen there, which means you can oxidize that, just like you can oxidize using Tollens or using Fehling for the methanoic acid there. So 2 and 3 give you option C there. Question 38, so each of these compounds you treat with excess NaBH4. This is a reducing agent. So the compound given below, they are all ketones or aldehydes. So NaBH4 can reduce both ketone and aldehyde. It cannot reduce carboxylic acid, not strong enough. To do reduction of carboxylic acid, you need lithium aluminum hydride. Anyway, the product of each reaction, you heat it with excess concentrated H2SO4. So what you actually get is you get dehydration after you form the alcohol. So what I'm going to do is I'm going to form the alcohol just like that, because then I'm going to do the elimination a little bit. So I'm just going to reduce it such that there's one hydrogen there, and then I've added the hydrogens on the carbonyl, giving me the alcohol, the corresponding alcohol. Okay, so we'll start from the alcohol. And now we're going to do dehydration. We're going to remove 2 H2O. So we have to remove 2 of the H2O, but this question is tricky because only one final product. So you're looking for something that will eliminate water to give you only one final product with this C7H10. So when we do elimination, we have to go to the next carbon. So this is the carbon with the OH. We're looking at the next carbon. This is a CH2. This is also a CH2, but this CH2 is next to something that has OH. This CH2 is not next to something that has OH. These two CH2 are different. So when I eliminate that, and for this one I have no choice because this is only next to one carbon. So I definitely have this thing which have no choice. But then you also imagine that you could have the hydrogen, the pink color one now, on the other carbon to give you the double bond on this side instead of on that side. By looking at that, I can tell you that I will have 2 different alkenes, so not one different alkene. And having done that, well, one cannot give me one final product. If I show you, you will understand what I'm talking about. So this alkene at the bottom, I have no choice. But this alkene here, the double bond there, is a result of removing this H and OH. I get a double bond there. And then if I draw a green color one, so I get an alkene at the bottom, no choice from there, but I get a double bond there between this H and between these 2 carbons because of removing this H and the OH next to each other. And guess what? These are 2 different alkene. So there are 2 different alkene products, but you only want one final product, so one cannot be the answer that you're looking for. It's so coincidentally that I was just looking at number 1 as something that is giving me 2 different products, and that's how I could spot the answer. Then number 1 cannot be correct. If number 1 cannot be correct, your option really is quite limited. You're left with 2 and 3, which is option number C. Anyway, I'm doing a tutorial, so my job really is to show you how they are not the answer or how they are the answer. So here you have a symmetrical structure. So in terms of the symmetrical structure, that means, well, going back to this hydrogen here, the CH2 here is the same as this CH2 because here it's 1, 2, 3 like that away from that. If you are here, you are 1, 2, 3 away from that. This is a totally symmetrical structure. So I could get this one, which is the same as removing from the other side. So I could draw I could draw what I'm gonna get. This one is exactly the same as this one. They are the same, which is why there's only one product there. Okay, now let's do the third one and show you and convince ourselves. What do we have here? Here and here. So you might be thinking, oh, this one can remove from here, but this one can also remove from there. Then they will give me two different alkene. However, if you look at the question, C7H10, that means you must remove both the OH. If you use this OH and this H, that means this OH here will not have any other hydrogen to remove, because carbon from 4 bond 1, 2, 3, there is only one hydrogen there. There is no choice for you except to remove those things there, which means there is no more hydrogen for this to choose from on this carbon, and therefore you have to choose the hydrogen on the other side, meaning to say you have no other choice. No other choice, well, therefore you're left with one product. Just like that, one product, 2 and 3 is definitely what you're looking for. But if you check number one cannot be correct because two different alkene products. Therefore, leaving you 2 and 3 must be the correct answer without even checking. Question 39, which reaction results in the formation of propanoic acids? So this is a 3-carbon acid. If we look at option 2 first, we have a CH3, CH3. We have a hot concentrated H plus acidified KMnO4. This is the rupture, the oxidative rupture of carbon-carbon double bond, case study under oxidation of alkene. So you're going to break and rupture that. This is a RCH double bond. They will give you the carboxylic acid, so CH3COOH. Whereas this side is also a RCH double bond. They will also give you the carboxylic acid, so COOH, CH3. And guess what? Both of them are 2-carbon carboxylic acid. So none of them is a 3-carbon carboxylic acid. Number 2 is wrong. Therefore, only one can be correct there. Hopefully that makes sense, yeah? As for why one is correct, so this is an ethanoate. So it's a salt. As you can imagine, it's a plus on the sodium, minus on the carboxylate. When you just protonate means you just accept the protons, because this is a base, it just accepts the proton, and you will get 3-carbon carboxylic acid, which is propanoic acid. On the other hand, you also have option number 3, which is definitely wrong. This is ethanol. And when you do oxidation of the ethanol, using the acidified dichromate 6, which is orange in color, you will get this orange turning green, as this will form the chromium plus 3. So chromium plus 6 in the Cr2O7 minus acidified, that is orange color. As it acts as an oxidizing agent, itself will get reduced to this green color solution, which is chromium 3 plus aqueous. This is how you represent oxidation number, although these are the species responsible for the specific color there. Okay, so the ethanol is going to go to 2 carbons carboxylic acid if you reflux it. If you heat and distill immediately, you won't get the acid, you'll just get the aldehyde if you heat and distill immediately. Regardless, both of them will just be 2-carbon carboxylic acid, leaving you D as the only possible answer. Question 40, we come to the end of this paper now. This is propanamide. So this is an amide. CONH is what you call an amide, something you have done and come across in your O level, GCSE or IGCSE level towards the end of your organic chemistry. This is about hydrolysis of the propanamide. Just like hydrolysis of ester, you can also hydrolyze amide, just where at the bond where you form it. So that bit there on the left hand side has got the carbonyl, so that will give you the carboxylic acid fragment. On the right hand side, that will give you the NH, that will give you what you call the amine fragment. Amine, not amide, but when they condense together with carboxylic acids, they give you an amide. Now looking at option number 2, since they want the correct statement, propanamide can be hydrolyzed under reflux with NaOH. Yes, this is called base hydrolysis. Just like you could do base hydrolysis of ester, you could also do it for amide, you could also do it for nitriles. Okay, you can be hydrolyzed by heating with H2SO4 aqueous. Yes, that is called acid hydrolysis. You could get acid hydrolysis of esters, you could get acid hydrolysis of nitriles, you could also get acid hydrolysis of amide. The most important thing really is, if you do it under base hydrolysis, you will not get the acid. Instead, what you will get is, you will get the salt of the acid because the carboxylic acid is acidic. It will be deprotonated, but you will get the NH3 unreacted with the NOH because that one is basic, that one is basic. On the other hand, if I do this acid hydrolysis, I will get NH4 plus and then twice SO4 because this is the salt that your base will form with the acid. But of course, I will get the carboxylic acid, which is the propanoic acid, 3-carbon acid there. Now 1 and 2 are correct. How about the last one? Can be hydrolyzed by cold water. That doesn't happen. Think about your amino acids condensing to give you proteins. Your dipeptide in your body doesn't get hydrolyzed just because they have water, but they do need enzymes and various other conditions to make it happen in the body. Okay, so 3 is definitely wrong. So only 1 and 2, there is option B there. Okay, we reached the end of this paper, paper 1-1 for this November 15th, Cambridge International A-Level MCQ, of which the curriculum is going to be suitable for anyone doing this 16 to 18 years old chemistry curriculum all around the world. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And don't forget that only the silver tier members will be able to access these full paper tutorials. So do spread the word, and if it does help other people, it only costs a cup of coffee to upgrade to a silver tier membership, either directly or via VPN. So do consider upgrading to enjoy all these privileges. Thank you for watching, and I'll see you in the next tutorial video.